All right. Hi, everybody. We're going to be talking about kind of the big first application of integration, which is talking about the net change theorem. And this is kind of useful from FTC part two. So, meaning we're going to be needing to calculate an integral over a certain period that's going to give us either a total distance or a net rate of change. So, we're going to be kind of talking about this in two pieces. We're going to be talking about what the difference between displacement and total distance is going to be. And I apologize about the quality of this camera. This is my old camera that I have at home. It's a little bit blurry, kind of out of focus sometimes. Just bear with me. So the first thing we're going to be talking about is displacement, which is basically the integral of velocity, which gives us the net change in position. So I'll kind of give you what that means in terms of symbols and equations first, and then I'll kind of show you what that means graphically. So this integral of velocity on the time period from t sub 1 to t sub 2 of, this velocity function, whatever that is, can tell us that this is really the same thing as the integral from t sub 1 to t sub 2 of s prime of t. Because remember that velocity is really the derivative of our position function, which really tells us that we're calculating the antiderivative of s prime, which is really s of t, from t sub 1 to t sub 2, which is really the FTC part 2 here. When we take an antiderivative of a derivative, we get that original function back, which is s of t, and we're evaluating it from t sub 1 to t sub 2, which really tells us that we're taking our position function and evaluating it from t sub 2 and subtracting our position function evaluated at t sub 1. So what this means graphically is if I were to just kind of take myself any function here, I'm just going to draw some kind of curve here. And here's t sub 1, here's t sub 2 over here. And say the curve looks something like this. I had part of the curve above the x-axis, I had part of the curve below the x-axis. Well, we know that integration is really talking about the area under the curve. So here, from t sub 1 to this x-intercept, I have positive area under the curve. From this x-intercept to t sub 2, I've got negative area under the curve. And basically what the net area does is it sums the total of the positive and the negative area together. So this is a total of the positive and the negative area. And it just gives us a net area. So positive and negative added together. The total area could be positive or it could be negative depending on what area there's more of. If there's more under the curve, the total net area is going to be negative. If there's more above the x-axis, the net area is going to be positive. And something that's a little bit different is the total distance, because the total distance actually needs to have some consideration of actually where the object is moving to the right, or where the v of t function is above the x-axis and moves to the left, or where the v of t is below the x-axis. So the total distance traveled is actually going to be the absolute value of this integral that we talked about in the first part here. And the way that we split that up, and we are going to have to split that up, is going to be into, depending on what the function is, usually two integrals, could be more. We're going to split that up into two integrals. I'll write this as t sub 1 to x of v of t dt plus some integral from x to t sub 2 v of t dt. And what this accounts for is, say that this first integral accounts for the area above the curve or above the x-axis, and say that this is my integral for the area that falls below the x-axis. What I need to account for is any area that's below the x-axis, I actually have to take the absolute value of this to make it be positive. So in the, actually before I talk about that, these x values, what do these x values stand for? The x's are actually where the particle changes direction. So x is where the particle changes direction. And the way that we can find that is by actually setting our v of t equal to 0. Because remember that when v of t equals 0, that's where our object or particle changes direction. So what this really means in terms of like graphs, if I go back up to this graph up here, what this would really mean is if I were to find the total distance traveled, I would really be taking this positive area above the curve, and I would actually be flipping this area to be above the curve so I could sum them together as positive values rather than keeping this one negative as we do when we were talking about the net area. So think about like us flipping negative area up into the positive quadrant and making it positive and then adding it together to our other positive area. So let's look at some examples. For example, one, I'm going to give you guys the velocity function, and we're looking for both displacement and total distance. Displacement is basically just FTC part 2. You don't have to worry about what's above or below the x-axis. You're literally just taking whatever the integral is, and you're basically just taking the antiderivative and evaluating it. So the displacement is usually the easier part. So if I have a v of t function, this is the function that I need to kind of begin with, because if I'm talking about displacement, the setup that we talked about up here says I need to take the integral of v of t. So my integral that I'm going to set up here, since I'm given v of t to find the displacement, so we'll start displacement here, is actually going to be the integral from t is equal to 1 to t is equal to 6, so 1 to 6, of this v of t function, which is t squared minus 2t minus 8 dt. And this is basically asking me to use part 2 of FTC. I need to find the antiderivative of this, and then I'm going to evaluate it from 1 to 6. So it looks like my antiderivative here is going to be 1/3 t cubed minus t squared minus 8t, and then I'm going to evaluate it from 1 to 6. So that means I'm going to take my 6, so 1/3 times 6 cubed minus 6 squared minus 8 times 6. And I'm going to subtract that evaluated at 1. So 1/3 times 1 cubed minus 1 squared minus 8 times 1. And then from there, just a matter of simplification. So let's see. I'm just going to use my calculator quick just to kind of move things along here. So 1/3 times 6 cubed looks like it's going to be 72 minus 36 minus 48. And then this is going to be, let's see, 1/3 minus 1 minus 8. So it looks like that should give us, let's see, -12 for this quantity. And I'm subtracting from that, let's see, it'll be 1/3 minus 1 minus 8. And that'll be -26 thirds. So this looks like I'm really taking -12 and adding 26 thirds to it. Which looks like it gives us a displacement of -10 thirds. And my units here should be whatever the distance is that I'm given, or my units of distance. So it looks like -10 thirds meters. Like I said, the displacement or the net area is going to be either negative or positive depending on how much area is below the curve or above the curve. So this looks like this function would have more area below the curve since the net distance is negative. So now I'm looking to say, okay, now that I've done my displacement, I need to do my total distance. And my total distance is going to be the integral from 1 to something of this v squared, v of t, dt, and then plus the integral from something to 6 of this v of t. So the question is, well, what is this value? Like what am I splitting my v of t into? Well, the first thing I need to know is what is v of t, or where is v of t equal to 0? Because that's going to tell me what these numbers are going to be. So that's the first thing I should be asking myself is, where is v of t equal to 0? So if I set up my v of t function, that's 2t squared minus 2t minus 8, set that equal to 0. That looks like it's going to give us t minus 4 times t plus 2. And that should give me two different t values, but it's telling us that t has to be positive because we're really just concerned about from 1 to 6 anyway. So I don't have to worry about this -2. So then once I know that 4 is going to be kind of that magic number that I have to put in for my upper and lower bounds, I need to figure out which one of these is going to produce the area that's negative or that's underneath the x-axis. So here's where my sign chart's going to come in. And I'm going to start my sign chart at the t-value of 1, and I'm going to end it at the t-value of 6. And I'm going to put 4 in the middle because that's the place where my particle or whatever is changing directions. And I need to figure out what is the sign of v of t here. So I'm going to pick a value in between here, and I'm going to plug, let's see, I'll just use 2. I'm going to plug 2 into here. I'm going to determine what my signs are. So 2 minus 4 is going to give me negative. 2 plus 2 is going to give me positive. So it looks like this one's going to be negative. If I plug in a 5, 5 minus 4 is positive. 5 plus 2 is positive. This is going to give me positive. So this is the area under the x-axis where my v of t is negative, and this is my area that's above the x-axis. So when I'm looking for where I'm putting my absolute values, it's going to be this integral from 1 to 4 because this is the area that's underneath the x-axis. So here is where I'm going to set up my absolute value because I want to make sure that this stuff is positive even though it's underneath the x-axis. So I'm going to have to set up my integral or my antiderivatives in 2 different pieces. I need to take the antiderivative of this v of t and then evaluate it from 1 to 4, and then take the antiderivative of the v of t and evaluate it from 4 to 6 and add those 2 things together. So the nice thing is we actually already know what our antiderivative is. We found that in the last problem. It's still 1/3 t cubed minus t squared minus 8t. So I'm going to first evaluate that from 4 to 1. So 1/3 times 4 cubed minus 4 squared minus 8 times 4. Subtracting from that, 1/3 times 1 cubed minus 1 squared minus 8 times 1. And this stuff is all going to be in absolute values because whatever that value is has to be positive because we have to move it again, kind of think about it as flipping it up from underneath the x-axis to above the x-axis. But then I have to add to that the FTC part 2 of this integral up here. So I'm going to take my antiderivative, evaluate it from 6. So 1/3 times 6 cubed minus 6 squared minus 8 times 6. And we're going to subtract that evaluated at 4. So 1/3 4 cubed minus 4 squared minus 8 times 4. And I'm just going to do a little simplification here. And the nice thing is from the displacement, we actually already know what this value is. And I think what this value is. So I'm really only going to be calculating out this. That's going to be new. So let's see, 4 cubed divided by 3. That's going to stay 64/3. Minus 16 minus 32. And I know that this quantity is negative 26/3 because we calculated that in the displacement part. And then I'm going to simplify this over here, which I actually already know is negative 12, which I calculated again in the displacement part. And then this is actually going to be, looks like the same calculation as this. So 64/3 minus 16 minus 32. So I think this ends up being, let's see, 112/3. And then we're adding 26/3. This is still all in absolute values. And then this is going to be adding negative 12. And then minus, again, I think that's 112/3. So I think when you add 112/3 and 26/3, I believe this gives us 46. And then we're technically subtracting 12 and then subtracting 112/3. So let's see, 46 minus 12 minus 112/3. Actually, hang on. Okay, let's see. Oops, I think it should be negative 80/3. Okay, made a little algebra mistake there. I think this should be 80 thirds, which would mean that this should be negative 80 thirds. Which means scratch that. Okay, yeah, so when we add those together, I believe that gives us the absolute value of negative 18, and then we're subtracting 12, and then we're adding 80 thirds. So it should give us positive 18 minus 12, and then plus 80 thirds. And I think when you add that together, that should give us 98 over 3. And since we're talking total distance, our units again should be meters. All right, we'll look at one more example here. This one is actually giving us an acceleration function and an initial velocity. So first thing I need to do is actually need to figure out what the velocity function is, because in order to do total distance, I need to know what the velocity is, because the total distance, remember, is the integral of the absolute value of velocity. So here's where kind of those initial conditions come back, and I need to work backwards from a of t, which is 2t plus 3. And I need to take the antiderivative of that to get velocity, which looks like it's going to be t squared plus 3t plus some c. And I need to solve for c by using my initial condition of v of 0 is equal to negative 4. So I'll plug in negative 4, plug in 0 for all my t's. So it looks like c is equal to negative 4. So that tells me that my velocity function is going to be t squared plus 3t and then minus 4. So here's part A. There's my velocity function. This is what I'm going to need to use in part B to find total distance. So my total distance here, and we're talking total distance here, so this is going to be, again, the absolute value that we have to worry about. So my total distance is going to be, looks like times from 0 to 10. So 0 to something of this v of t, so t squared plus 3t minus 4 dt. And then the integral from something to 10 of the t squared plus 3t minus 4 dt. So first thing I need to figure out, what are these values that I need to fill in here? So I need to figure out where is v of t equal to 0. So my v of t is going to be t squared plus 3t minus 4. If I factor that out, that should give me, let's see, t plus 4 times t minus 1, which should give me 2 t values. But again, I'm only worried about from 0 to 10. So negative 4 doesn't mean anything to me. So it must mean 1 is this value that I'm filling in. But again, I need to figure out which one I'm putting into absolute values. So I'm going to make myself a little sign chart here for v of t from 0 to 10. The value that I'm worried about is 1. So if I fill in, let's see, 1/2. 1/2 plus 4 is positive. 1/2 minus 1 is negative. If I fill in a 2, 2 plus 4 is positive. 2 minus 1 is still positive. So here, the 0 to 1 is the one that's under. The 1 to 10 is the one that's above. So this is going to be the integral that I'm, again, putting into absolute values. So my total distance is going to be the absolute value of the integral from 0 to 1 plus the integral from 1 to 10. So I need to find myself an antiderivative here. My antiderivative looks like it's going to be, let's see, 1/3 t cubed plus 3/2 t squared minus 4t. And I'm going to have to evaluate that from 0 to 1, and again, in absolute values. And then evaluate 1/3 t cubed plus 3/2 t squared minus 4t from 1 to 10. So I'll do that work down here on the bottom. Leave myself a little bit of room. So let's see, I'll start with 1/3 times 1 cubed plus 3/2 times 1 squared minus 4 times 1. And then the nice thing about this is when I evaluate that at 0, it's actually literally just minus 0. Because if I plug in zeros here, everything just goes to 0. And again, this is the part that I'm putting in absolute values. So then my second part here is to take that and evaluate it at 10. So 1/3 times 10 cubed plus 3/2 times 10 squared minus 4 times 10. And then subtract that quantity evaluated at 1. So it's going to be 1/3 plus 3/2 and then minus 4 by plugging 1 for all of my t's there. So then I'm going to go ahead and do some simplifying. So let's see, use my calculator here for just some quick calculations. This is going to give me negative 13 over 6 minus 0. So all this stuff is negative 13 minus 6, I believe. Let me just double check. 1/3 plus 3/2 minus 4. Yep. And then I'm going to evaluate my 1 at 10 next. So it looks like this is going to be 1,000 thirds. Let's see, 10 squared, 100 times 3 divided by 2 looks like it's going to be 150. And then minus 40. And again, I'm subtracting. This, I think, is negative 13 over 6. So it's going to give me the absolute value of 13 over 6. Plus, let's see, 1,000 thirds plus 150 minus 40. That's 1330 over 3. And then plus 13 over 6. Quickly add these up. And it looks like that's going to be 1343 over 3. And my units here, I'm not sure I'm giving units, so units. My total distance, 1343 over 3 units. All right, so it's going to be your turn to do some practice. Let me know if you have any questions, and I will see you guys tomorrow.